In mathematics, an equivalence relation is a binary relation that is at the same time a reflexive relation, a symmetric relation and a transitive relation. As a consequence of these properties, an equivalence relation provides a partition of a set into equivalence classes. Notation. Although various notations are used throughout the literature to denote that two elements A and B of a set are equivalent with respect to an equivalence relation R, the most common are a tilde B and a B, which are used when R is the obvious relation being referenced, and variations of a tilde RB, ARB, or ARB otherwise. Definition. A given binary relation tilde on a set X is said to be an equivalence relation if and only if it is reflexive, symmetric and transitive, that is, for all A, B and C in X. A tilde A, reflexivity. A tilde B if and only if B tilde A, symmetry. If a tilde B and B tilde C, then a tilde C. Transitivity. X together with the relation tilde is called a setoid. The equivalence class of A, displaystyle A, and a tilde, denoted A, displaystyle A, closing curly bracket, is defined as A equals, opening curly bracket, B, X, A, B, closing curly bracket, displaystyle A, equals B in X mid A, sim B. Examples. Simple example. Let the set, opening curly bracket, A, B, C, closing curly bracket, display style A, B, C, have the equivalence relation, opening curly bracket, A, B, B, C, C, B, C, C, B, closing curly bracket, display style A, B, B, C, C, B, C, C, B, backslash closing curly bracket, closing curly bracket. The following sets are equivalence classes of this relation. A equals, opening curly bracket, A, closing curly bracket, B, equals, C, equals, opening curly bracket, B, C, closing curly bracket, display style, A, equals, A, tilde 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 tilde, B, equals, C, equals, B, C. The set of all equivalence classes for this relation is, opening curly bracket, A, closing curly bracket, opening curly bracket, B, C, closing curly bracket, display style A, B, C. Equivalence relations. The following are all equivalence relations. Has the same birthday as, on the set of all people. Is similar to, on the set of all triangles. Is congruent to, on the set of all triangles. Is congruent to, modulo n, on the integers. Has the same image under a function, on the elements of the domain of the function. Has the same absolute value, on the set of real numbers. Has the same cosine, on the set of all angles. Relations that are not equivalences. The relation between real numbers is reflexive and transitive, but not symmetric. For example, 7 5 does not imply that 5 7. It is, however, a total order. The relation has a common factor greater than 1 with between natural numbers greater than 1. Is reflexive and symmetric, but not transitive. Example, the natural numbers 2 and 6 have a common factor greater than 1. And 6 and 3 have a common factor greater than 1. But 2 and 3 do not have a common factor greater than 1. The empty relation R on a non-empty set X, i.e., ARB is never true, is vacuously symmetric and transitive, but not reflexive. If X is also empty, then R is reflexive. The relation is approximately equal to, between real numbers, even if more precisely defined, is not an equivalence relation. because although reflexive and symmetric, it is not transitive, since multiple small changes can accumulate to become a big change. However, if the approximation is defined asymptotically, for example by saying that two functions f and g are approximately equal near some point if the limit of f minus g is 0 at that point, then this defines an equivalence relation. Connections to other relations. A partial order is a relation that is reflexive, antisymmetric, and transitive. Equality is both an equivalence relation and a partial order. Equality is also the only relation on a set that is reflexive, symmetric and antisymmetric. In algebraic expressions, equal variables may be substituted for one another, a facility that is not available for equivalence-related variables. The equivalence classes of an equivalence relation can substitute for one another, but not individuals within a class. A strict partial order is a reflexive, transitive, and asymmetric. A partial equivalence relation is transitive and symmetric. Transitive and symmetric imply reflexive if and only if for all x there exists a bx such that a tilde b. A reflexive and symmetric relation is a dependency relation, if finite, and a tolerance relation if infinite. A preorder is reflexive and transitive. A congruence relation is an equivalence relation whose domain X is also the underlying set for an algebraic structure, and which respects the additional structure. In general, congruence relations play the role of kernels of homomorphisms, and the quotient of a structure by a congruence relation can be formed. In many important cases, congruence relations have an alternative representation as substructures of the structure on which they are defined. E.g., the congruence relations on groups correspond to the normal subgroups. Any equivalence relation is the negation of an apartness relation, though the converse statement only holds in classical mathematics, as opposed to constructive mathematics, since it is equivalent to the law of excluded middle well-definedness under an equivalence relation. If tilde is an equivalence relation on X, and P, X, is a property of elements of X, such that whenever X tilde Y, P, X, is true if P, Y, is true, then the property P is said to be well-defined or a class invariant under the relation tilde. A frequent particular case occurs when f is a function from X to another set Y. If x1 tilde x2 implies f x1 equals f x2, then f is said to be a morphism for tilde, a class invariant under tilde, or simply invariant under tilde. This occurs, e.g., in the character theory of finite groups. The latter case with the function f can be expressed by a commutative triangle. See also invariant. Some authors use compatible with tilde or just respects tilde instead of invariant under tilde. More generally, a function may map equivalent arguments under an equivalence relation tilde a to equivalent values under an equivalence relation tilde b. Such a function is known as a morphism from tilde a to tilde b. Equivalence class, quotient set, partition, let a, b, x, display style a, b in X. Some definitions. Equivalence class, a subset Y of X such that a tilde b holds for all a and b in Y, and never for a in Y and b outside Y, is called an equivalence class of X by tilde. Let a equals, opening curly bracket, X, X, a, X, closing curly bracket, display style, a, equals X, in X, mid a, sim X. Denote the equivalence class to which A belongs. All elements of X equivalent to each other are also elements of the same equivalence class. Quotient set, the set of all possible equivalence classes of X by tilde, denoted X slash equals opening curly bracket x closing curly bracket display style x method sim equals x mid x in x is the quotient set of x by tilde. If X is a topological space, there is a natural way of transforming X tilde into a topological space. See quotient space for the details. Projection. The projection of tilde is the function pi x slash display style pi x to x method sim defined by pi x equals x display style pi x equals x closing curly bracket, which maps elements of X into their respective equivalence classes by tilde. Theorem on projections. Let the function f x b be such that a tilde b f a equals f b. Then there is a unique function g x tilde b such that f equals g pi. If f is a surjection and a tilde b left right arrow f a equals f b, then g is a bijection. Equivalence kernel. The equivalence kernel of a function f is the equivalence relation tilde defined by x y f x equals f y display style x sim y iiff x equals f y closing curly bracket. The equivalence kernel of an injection is the identity relation. Partition. A partition of X is a set P of non-empty subsets of X, such that every element of X is an element of a single element of P. Each element of P is a cell of the partition. Moreover, the elements of P are pairwise disjoint and their union is X equals counting possible partitions equals. Let X be a finite set with n elements. Since every equivalence relation over X corresponds to a partition of X, and vice versa, the number of possible equivalence relations on X equals the number of distinct partitions of X, which is the nth Bell number Bn. B n equals 1, e k equals 0, infinity, k n k display style b underscore n equals frac 1 e sum underscore k equals 0 caret inf d frac k caret n k closing curly bracket closing curly bracket closing curly bracket, where the above is one of the ways to write the nth Bell number. Fundamental theorem of equivalence relations. A key result links equivalence relations and partitions. An equivalence relation tilde on a set X partitions X. Conversely, corresponding to any partition of X, there exists an equivalence relation tilde on X. In both cases, the cells of the partition of X are the equivalence classes of X by tilde. Since each element of X belongs to a unique cell of any partition of X, and since each cell of the partition is identical to an equivalence class of X by tilde, each element of X belongs to a unique equivalence class of X by tilde. Thus there is a natural bijection between the set of all possible equivalence relations on X and the set of all partitions of X. Comparing equivalence relations. If tilde and approximately equals are two equivalence relations on the same set S, and a tilde B implies A approximately equals B for all A, BS, then approximately equals is said to be a coarser relation than tilde, and tilde is a finer relation than approximately equals. Equivalently, tilde is finer than approximately equals if every equivalence class of tilde is a subset of an equivalence class of approximately equals, and thus every equivalence class of approximately equals is a union of equivalence classes of tilde. Tilde is finer than approximately equals if the partition created by tilde is a refinement of the partition created by approximately equals. The equality equivalence relation is the finest equivalence relation on any set, while the trivial relation that makes all pairs of elements related is the coarsest. The relation tilde is finer than approximately equals on the collection of all equivalence relations on a fixed set is itself a partial order relation, which makes the collection a geometric lattice, generating equivalence relations. Given any binary relation A x times x, display style A subset x times x on x, display style x, the equivalence relation generated by A display style A is the intersection of the equivalence relations on x, display style x, that contain A display style A, since x times x, display style x times x, is an equivalence relation. The intersection is non-trivial. Given any set X, there is an equivalence relation over the set XX of all possible functions XX. Two such functions are deemed equivalent when the respective sets of fixed points have the same cardinality, corresponding to cycles of length 1 in a permutation. Functions equivalent in this manner form an equivalence class on XX, and these equivalence classes partition XX. An equivalence relation tilde on X is the equivalence kernel of its surjective projection pi XX tilde. Conversely, any surjection between sets determines a partition on its domain, the set of preimages of singletons in the codomain. Thus an equivalence relation over X, a partition of X, and a projection whose domain is X are three equivalent ways of specifying the same thing. The intersection of any collection of equivalence relations over X, binary relations viewed as a subset of X times X, is also an equivalence relation. This yields a convenient way of generating an equivalence relation. Given any binary relation R on X, the equivalence relation generated by R is the smallest equivalence relation containing R. Concretely, R generates the equivalence relation A tilde B if and only if there exist elements x1, x2, xn in X such that A equals x1, B equals xn, and she plus 1, R or she plus 1, she, R, I equals 1, n1. Note that the equivalence relation generated in this manner can be trivial. For instance, the equivalence relation tilde generated by any total order on X has exactly one equivalence class, X itself, because X tilde Y for all X and Y. As another example, any subset of the identity relation on X has equivalence classes that are the singletons of X. Equivalence relations can construct new spaces by gluing things together. Let X be the unit Cartesian square O1 times O1, and let tilde be the equivalence relation on X defined by A, B, O1, A, 0, tilde, A, 1, 0, B, tilde, 1, B. Then the quotient space X tilde can be naturally identified. Homeomorphism. With a torus, take a square piece of paper, bend and glue together the upper and lower edge to form a cylinder. Then bend the resulting cylinder so as to glue together its two open ends, resulting in a torus. Algebraic structure. Much of mathematics is grounded in the study of equivalences and order relations. Lattice theory captures the mathematical structure of order relations. Even though equivalence relations are as ubiquitous in mathematics as order relations, the algebraic structure of equivalences is not as well known as that of orders. The former structure draws primarily on group theory and, to a lesser extent, on the theory of lattices, categories, and groupoids. Group theory. Just as order relations are grounded in ordered sets, Sets closed under pairwise supremum and infimum. Equivalence relations are grounded in partitioned sets, which are sets closed under bijections and preserve partition structure. Since all such bijections map an equivalence class onto itself, such bijections are also known as permutations. Hence permutation groups, also known as transformation groups, and the related notion of orbit shed light on the mathematical structure of equivalence relations. Let tilde denote an equivalence relation over some non-empty set A, called the universe or underlying set. Let G denote the set of bijective functions over A that preserve the partition structure of A. X A G G, G, X, X. Then the following three connected theorems hold. Tilde partitions A into equivalence classes. This is the fundamental theorem of equivalence relations, mentioned above. Given a partition of A, G is a transformation group under composition, whose orbits are the cells of the partition. Given a transformation group G over A, there exists an equivalence relation tilde over A, whose equivalence classes are the orbits of G. In sum, given an equivalence relation tilde over A, there exists a transformation group G over A whose orbits are the equivalence classes of A under tilde. This transformation group characterization of equivalence relations differs fundamentally from the way lattices characterize order relations. The arguments of the lattice theory operations meet and join our elements of some universe A. Meanwhile, the arguments of the transformation group operations composition and inverse are elements of a set of bijections A. Moving to groups in general. Let H be a subgroup of some group G. Let tilde be an equivalence relation on G, such that a tilde be left-right arrow. Ab -1 H. The equivalence classes of tilde, also called the orbits of the action of H on G, are the right cosets of H in G. Interchanging A and B yields the left cosets. Proof. Let function composition interpret group multiplication, and function inverse interpret group inverse. Then G is a group under composition, meaning that X A G G, G, X, equals X, because G satisfies the following four conditions. G is closed under composition. The composition of any two elements of G exists, because the domain and codomain of any element of G is A. Moreover, the composition of bijections is bijective. Existence of identity function. The identity function, I, X, equals X, is an obvious element of G. Existence of inverse function. Every bijective function G has an inverse G-1, such that G-1 equals I. Composition associates. F, G, H, equals F, G, H. This holds for all functions over all domains. Let F and G be any two elements of G. By virtue of the definition of G, G, F, X, equals F, X, and F, X, equals X, so that G, F, X, equals X. Hence G is also a transformation group, and an automorphism group, because function composition preserves the partitioning of A. White medium square, display style, square. Related thinking can be found in Rosen. 2008. CHPT. 10. Categories and groupoids. Let G be a set and let tilde denote an equivalence relation over G. Then we can form a groupoid representing this equivalence relation as follows. The objects are the elements of G, and for any two elements X and Y of G, there exists a unique morphism from X to Y if and only if X tilde Y. The advantages of regarding an equivalence relation as a special case of a groupoid include: whereas the notion of free equivalence relation does not exist, that of a free groupoid on a directed graph does. Thus it is meaningful to speak of a presentation of an equivalence relation, i.e., a presentation of the corresponding groupoid. Bundles of groups, group actions, sets, and equivalence relations can be regarded as special cases of the notion of groupoid, a point of view that suggests a number of analogies. In many contexts, quotienting, and hence the appropriate equivalence relations often called congruences, are important. This leads to the notion of an internal groupoid in a category. Lattices, the possible equivalence relations on any set X, when ordered by set inclusion, form a complete lattice, called conx by convention. The canonical map Ker x caret x con x relates the monoid x caret x of all functions on X and con X. Ker is surjective but not injective. Less formally, the equivalence relation Ker on X takes each function f x to its kernel Ker f. Likewise, Ker is an equivalence relation on X caret X. Equivalence relations are mathematical logic. Equivalence relations are a ready source of examples or counterexamples. For example, an equivalence relation with exactly two infinite equivalence classes is an easy example of a theory which is omega categorical, but not categorical for any larger cardinal number. An implication of model theory is that the properties defining a relation can be proved independent of each other, and hence necessary parts of the definition, if and only if, for each property. Examples can be found of relations not satisfying the given property while satisfying all the other properties. Hence the three defining properties of equivalence relations can be proved mutually independent by the following three examples. Reflexive and transitive, the relation on n, or any preorder. Symmetric and transitive, the relation R on n, defined as arb left right arrow ab does not equal 0, or any partial equivalence relation. Reflexive and symmetric, the relation R on z, defined as arb left right arrow a minus b is divisible by at least one of two or three, or any dependency relation. Properties definable in first-order logic that an equivalence relation may or may not possess include: the number of equivalence classes is finite or infinite. The number of equivalence classes equals the finite natural number n. All equivalence classes have infinite cardinality. The number of elements in each equivalence class is the natural number n. Euclidean relations. Euclid's the elements includes the following common notion 1. Things which equal the same thing also equal one another. Nowadays, the property described by common notion 1 is called Euclidean. Replacing equal by are in relation with by relation is meant a binary relation, in which arb is generally distinct from bra. A Euclidean relation thus comes in two forms: arc brc, arb, left Euclidean relation, CRA CRB, arb, right Euclidean relation. The following theorem connects Euclidean relations and equivalence relations. Theorem: if a relation is left or right, Euclidean and reflexive, it is also symmetric and transitive. Proof for a left Euclidean relation: arc brc, arb, ac, equals ara bra, arb, reflexive, a raised t, equals bra arb, hence R is symmetric. Arc brc, arb, symmetry, equals arc crb, arb, hence R is transitive. White medium square, display style underscore box, with an analogous proof for a right Euclidean relation. Hence an equivalence relation is a relation that is Euclidean and reflexive. The elements mentions neither symmetry nor reflexivity, and Euclid probably would have deemed the reflexivity of equality too obvious to warrant explicit mention. See also apartness relation, conjugacy class, equivalence, geometry. Topological conjugacy. Up to. Notes. Brown, Ronald. 2006. Topology and Groupoids. Booksurge LLC. ISBN 1-4196-2722-8. Castellani, E. 2003. Symmetry and Equivalence in Braiding. Catherine, and E. Castellani, eds. Symmetries in Physics. Philosophical Reflections. Cambridge Univ. Press. 422-433. Robert Dilworth and Crawley, Peter. 1973. Algebraic Theory of Lattices. Prentice Hall. CHPT. 12 discusses how equivalence relations arise in lattice theory. Higgins. P. J. 1971. Categories and Groupoids. Van Nostrand. Downloadable since 2005 as a TAC reprint. John Randolph, Lucas. 1973. A Treatise on Time and Space. London. Methuen. Section 31. Rosen, Joseph. 2008. Symmetry Rules. How Science and Nature are Founded on Symmetry. Springer Verlag. Mostly CHPTS. 910. Raymond Wilder. 1965. Introduction to the Foundations of Mathematics 2nd edition. Chapter 228. Axioms Defining Equivalence. pp. 48-50. John Wiley & Sons. Hayeswinkle. Michiel. ed. 2001. 1994. Equivalence Relation. Encyclopedia of Mathematics. Springer Science Plus Business Media B. V. Kluwer Academic Publishers. ISBN 978-1-55608-010-4. Bogomolny, A. Equivalence Relationship. Cut the Knot. Access 1 September 2009. Equivalence Relation at Planet Math. Binary matrices representing equivalence relations at OEIS.